Hey everyone, welcome. I am absolutely thrilled to have you here today. We're going to dive right into this whiteboard style explainer to really lock down those core science concepts you need for your Term 3 exams. We're going to clear up any confusion and get you perfectly prepped by walking through exactly what you need to know. So, here's our game plan. We're going to cover galaxies in our universe, exploring the solar system, gravity and its effects, and finally, Newton's laws of motion. All right, let's jump straight into part one, galaxies in our universe. It's time to understand the cosmos. Okay, let's start with a quick primer. You know, the universe contains literally trillions of galaxies. But what is a galaxy exactly? Well, it's basically a massive system made up of stars, gas, dust, and dark matter. And the whole shebang is held tightly together by gravity. Edwin Hubble actually classified these massive cosmic structures into three main shapes. First up, we've got spiral galaxies. Picture a central bulge with these radiating pinwheel-like arms full of young stars. Our very own Milky Way, yep, that's a spiral galaxy. Then we have elliptical galaxies. These look kind of like footballs, and they're mostly made up of older, redder stars without a whole lot of gas or dust. And lastly, irregular galaxies. Just like the name implies, these guys lack any sort of symmetrical shape. They are highly distorted and pretty chaotic. Let's test that out with a practice question, exactly like the kind you're going to see on your exam. So which statement defines galaxies correctly? Take a quick second. Is it A, B, C, or D? And the correct answer is B. Galaxies are huge collections of gas, dust, and stars held together by gravity. Gravity is absolutely the crucial universal glue here. The other options are just describing solar systems or individual stars, which are, way, way smaller in scale. Moving right along, let's hit section 2, exploring the solar system. We're zooming in on planets and orbits. This is such a brilliant illustration of our place in space, the heliocentric model. People used to actually think Earth was the center of everything, but we now know that Earth and the other planets travel in these curved elliptical orbits around the sun, and that motion is entirely driven by the sun's massive gravitational pull. Now, check out this data. When scientists measure these massive distances in our solar system, they use something called an AU, or astronomical unit. 1 AU is basically the average distance from the Earth to the sun. Look at Mercury, it's sitting pretty close at just 0.39 AU, and it zips around the sun in only 0.24 Earth years. But then jump way down to Neptune. It's way out there at 30.1 AU, and its orbital period is a massive 164 years. The pattern is crystal clear, right? As the distance from the sun increases, the time it takes to orbit increases too. Let's put that pattern recognition to the test. Based on what we literally just saw, which planet takes longer to complete one full orbit around the sun, Mercury or Neptune? If you guess Neptune, you absolutely nailed it. The answer is B. Because Neptune is so incredibly far away, it has a much longer orbital path to travel. Plus, being that far out means the sun's gravitational pull is weaker on it, making it a much, much longer journey to finish a single year. Okay, that brings us to section 3, gravity and its effects. Let's talk about this universal force. Now, listen up, because this is a super common trap on exams. People mix up mass and weight all the time in everyday conversation, but scientifically, they are entirely different things. Mass is just about the amount of matter in an object, period. It does not change whether you're standing on Earth, on the moon, or floating in deep space. Weight, on the other hand, depends on the gravitational force acting on that matter. So, say you have a 2-kilogram book sitting on your desk. Its mass is 2 kilograms, but its weight is calculated by how hard the Earth's gravity is pulling that 2 kilograms down toward its center. Let's lock this concept down with a quick fill-in-the-blank question. Mass depends on blank, and weight depends on blank. And the correct answer is D. Mass depends on the amount of matter, and weight depends on gravitational force. Keep that straight, and you are going to breeze right past one of the most common trick questions they'll throw at you. Finally, we have reached section 4, Newton's laws of motion. Let's see these forces in action. Okay, Newton's second law is absolutely crucial for your test. It gives us the exact mathematical relationship tying all this together. F equals m times a. That's net force, measured in newtons, equals mass, in kilograms, times acceleration. Simply put, if you want to accelerate something that has a lot of mass, you are going to need a ton of force. And then we have Newton's third law, which tells us that for every action force, there's an equal and opposite reaction force.
Now, there is a huge misconception here. A lot of people think, wait, if the forces are equal and opposite, shouldn't they just cancel each other out so nothing ever moves? Actually, scratch that. They never cancel out because they are acting on two entirely different objects. Think about a swimmer. The swimmer's hands push backward on the water. That's the action force. And the water pushes the swimmer's body forward. That's the reaction force. Two different bodies interacting to create forward movement.
Let's do a quick knowledge check to make sure that definition is really locked in before test day. The statement, "For every action there is an equal but opposite reaction," is defining which law?
Yep, the answer is D. That statement is the literal defining principle of Newton's third law. No trick to it.
Now let's apply it with some actual numbers, because that is exactly how you'll probably see it on the exam. If you push on a wall with a force of 30 newtons, what's the force acting on you from the wall? Is it A, B, C, or D? It's exactly 30 newtons, because according to the third law, the reaction force is always equal in strength and opposite in direction. You push with 30, the wall gives you 30 right back. And that brings us to the end of our whiteboard explainer. Just remember, mastering these foundational concepts, from the shapes of galaxies to the precise definitions of Newton's laws, is your golden ticket to acing this exam. You have all the tools you need right here. So, what fascinating part of science are we going to explore next? Keep learning, keep asking questions, and I'll see you in our next explainer.